Okay, so now we're going to look at one of the, I think it's a very cool problem with different aspects to it. Sort of brings in a lot of different items. So this is called the Brachistochrone problem. So this is stated sort of formally here, which is probably how they only stated things. Let's say we have a point A and a point that I will call B, and maybe just for the sake of having something definite, I will call this point 0 A. So the coordinates of this point are going to be 0, lowercase a, the x coordinate is 0, the y coordinate is lowercase a, and this coordinate here, I'm going to say that the x position is little b and the y position is 0, just to have something definite to work with. So maybe I need to label it more like this. Okay, in other words, this is starting at y equals 0 and x is equal to a. X equals 0 and y is equal to a, and then it ends at y equals 0 and x is equal to b. And we want to find the path. We want to find the curve along which, if you start a ball from here and let it slide down to there, is going to do it in the fastest amount of time. So again, we want the find the curve that when you start here and it when you drop an object from here and it slides along to that point right there, that is going to go in the fastest the shortest amount of time. Okay, so it's not a straight line. So it's not just the line segment connecting those 2 points. That's not going to get it the fastest. So the question is, what is the fastest? Well, Johann Bernoulli proposed this in 1696. The deadline was the end of that year. Nobody had responded, and so Leibniz says, well, you should wait. In January of the next year, he says, well, you should wait until Easter of this year, extend the deadline to Easter of this year, and that's exactly what Bernoulli did. And he offered here, I will just read out what I have here, a prize neither of gold nor silver, rather, since virtue itself is its own most desirable reward, and fame is a powerful incentive, we offer the prize compounded of honor, praise, and approbation. Thus we shall crown, honor, and extol publicly and privately in this letter and by word of mouth the perspicacity of our great Apollo. So, basically a bunch of fancy words for saying there's no actual prize. People will just think you're a real cool guy if you can solve this problem. Okay, well, remember, they still have this, feud going on between mathematicians in the continent and English mathematicians over which mathematician's conception of calculus is better, either Leibniz or Newton. There's still sort of a controversy that's going on during this time that we're discussing. So, Bernoulli sent this letter. He didn't think that either Newton didn't get it or he didn't think Newton got it. It appears that Newton didn't get it the first time Bernoulli issued this challenge. So Bernoulli mails it to Newton. Newton goes over this. Newton gets it when he gets home from work one day. And he was working at the Mint at this point in his career. He's no longer really working in math and physics anymore. Anyways, he gets the note and he stays up all night and solves the problem. Now, this is not what Leibniz wanted to happen. Leibniz and the Bernoullis wanted him to not be able to solve it, but he solved it because, even though he might be a jerk, he's still one of the smartest people that has ever lived, and so he solved it. Now, we're not going to look at his solution method today. Johann Bernoulli solved it, Jacob Bernoulli solved it, Leibniz solved it, and Newton solved it. Now, Johann Bernoulli uses a kind of a principle of least action, or that is, nature is going to do the thing that costs the least amount of whatever. Okay, that's how he solves this problem. Now, I'm going to post a video from the Veritasium YouTube channel where they go over the solution to this problem and actually go a little bit further than what we're going to talk about, and also will intersect with some of the other things that we're going to talk about. Jacob did something different. He solved this problem a little bit differently, and that's sort of the method that I want to look at to sort of understand how we could get a solution to this problem. I do need to look here in my notes because I think there was something else that I wanted to say, but I don't remember what it is now. Yeah. Okay, so there's a couple of things that I want to observe first. And this is kind of a very important principle for problems like this. So what we want to do is we want to think about having a curve going from here to here. I'm going to say that this is y is equal to some function of x. So y is equal to some function of x. And just like for the catenary problem, we can think about this curve as being a function of x because it's clearly not going to curve up around on itself. So this curve we can write as the graph of some function, y equals f of x. And now we want to figure out what that function is. So that's the goal here. We want to figure out what that function is. Now let's assume that this is the optimal path. So let's assume that this is the optimal path. So let's just think of some of the things that we can think about. Now, one thing that we can think about that's not going to be so important for this video, but is an important idea, is that each segment of the path must also be the shortest time path. And that's what I'm going to call the shortest time path instead of the Brachistochrone curve. If I look here and here, this path right there also has to be the least path between those 2 points right there. Well, why is that? Well, let's assume it's not. Let's assume there was another path, maybe something that looked like this. Maybe that actually was the shortest time path between these 2 points. Well, then what we could do is it seems like we could replace what we had before. Seems like we could replace that path with this shortest path, with this shorter time path between these 2 points right there. And now we know that this is going to be a shorter path. It seems like overall this should be a shorter path. Okay, and it is a shorter path. So definitely going from here to there will be a shorter path than going from here to there along the purple thing, if this blue line is the actual locally shortest path between these 2 points right there. But actually, here's what we know. We know that if this was the locally shortest path between these 2 points right here, then this new path going down the purple line over the blue line and then back down the purple line or purple curve and blue curve, that would be the overall. That would be overall a path that was shorter than the alleged shortest path right here. So why is that? The reason is that we know how long, if we know this path right there, and we know the speed of the ball at this point right here, that completely determines the length of time it'll take to go that distance right there. Okay, this is just sort of a classical mechanics thing. If I know how fast the ball is going here, that is, I know its momentum, and I know its position because it's right here, and I know it's going to go along that path right there, and I know everything I need to know about that path right there. Okay, like this path is fixed, then the only thing that will determine how fast it takes the ball or whatever to go from there to there is purely based on the speed at that point right there. Okay, so it could be the case. It could be the case that actually this blue line or this blue curve right there gives us a locally shorter path, but maybe at the expense of the speed of the ball at that point. So maybe going from here to there is going to take a longer amount of time than going from here and down on this blue curve to there. But maybe if you go from here to there along the purple curve, the ball's going faster here than it is if you go this shorter distance path. And then so overall, it could be that the total distance along the purple path is still going to be shorter than the distance along the purple path and then this blue path and then the purple path like that. Okay, just think through what I'm saying here. I hope you're doing that, but I know these explanations can get a little bit complicated. But here's what we know. We know that the velocity of the ball, or whatever is going down here, is proportional. I'm just going to use the constant of proportionality as the square root of a to the total distance that the ball has fallen. So when I say the total distance that the ball has fallen, I mean like this right here. That right there. That is the total distance that the ball has fallen. Okay. And so what it means is whether the ball goes this way or whether it comes down here and goes like that and then back up, the speed of the ball or the velocity of the ball is going to be proportional to that distance right there. Okay. So therefore, we know it's going to be, the speed of the ball is going to be the same whether it comes down this point right there or whether it comes down this point to the blue curve and like that. Okay, so in other words, we know that at this point right here, no matter which path it takes, its speed is going to be the same. Okay, so then therefore what that tells us is there's no way that we could sort of come down here, go on this blue curve, and then have a slower speed or a faster speed. So in other words, if each segment of this curve is not the local shortest time path, then we can always change each segment of the curve to whatever the local shortest time path is between 2 points, and that path will be shorter than what was alleged to be the shortest time path. In other words, the thing that was alleged to be the shortest time path is not the shortest time path. Okay, so here is, that is something that's going to be a little more important when we talk about Euler's approach to this problem. But now let's go back to the Bernoulli approach to the problem, or one of the approaches of the problem. Well, this is also important for the Bernoulli approach to the problem as well. These are all related ideas to each other, or these ideas, I should say, are all related to each other. Okay, so again, I think there might be something that I want to say that I am forgetting here, and I don't want to do that. Yeah, okay. So again, we're saying that y is equal to a here, and y is equal to 0 here. And then, let's see, I just realized that I have in my notes some of these slightly backwards. Okay, so the coordinate system can work out a little bit better. I'm going to change my labeling of these points right here because I want to make sure that I don't mess up what I have for the notes. So I'm actually going to say that this point right here is 0, 0. This point is 0, 0. And then this point right here, this will be lowercase b. And then I'm just going to call this, it doesn't matter what we call it, so I'm going to call it lowercase c. And what we're doing is we want the thing about the y direction as being positive in the downward direction. Okay, and this will make sense in just a little bit. Okay, so let's consider a piece like this. So we're going to look maybe at a segment that looks something like this. If S is the arc length of this, that is the distance from there to there, from here to here. Let's see, that is the distance from the beginning down this to that point right there. If that's equal to S, then again we can do our differential triangle. This is going to be ds, this is going to be dy, and this is going to be dx. Okay, now we know that the speed is distance over time, so we've got ds over dt. That's equal to speed. This is going to be equal to the square root of 2 times, or let me do it more generally, little a times y. And by the way, I mentioned this a minute ago that the velocity of the ball is going to be, that the velocity of the ball, really this is like the speed of the ball. The speed of the ball is going to be equal to or proportional to the distance that the ball has fallen, whatever is rolling here. Now this concept of proportionality will change depending on exactly what we're modeling here. if we model just something sliding down this, I don't know, like a thing, I don't know what it could be. I always think in terms of balls, but if we model something just sliding down, like a cube or something, just sliding down, then this A is going to be 2 times G. On the other hand, if we're thinking about something rolling down this, then what's going to happen is that this A is going to incorporate both the gravitational force, but remember there's also inertia, there's circular inertia and a moment of inertia due to rolling. So you might have seen experiments where like you have the same ramp and 2 different objects that weigh the same mass, but one object is like a ring. One we have like a ring and a disc that weigh the same mass or have the same mass going down a ramp, and the ring that has all of its mass concentrated on the outside there is going to roll slower than the disc. And so that would typically have to be taken into consideration here. But as long as the object stays the same, this A is going to stay the same. And the reason that this is true, the way that we can come up with this, Galileo came up with it one way, but the way that I want to mention it is that it's just due to conservation of energy. So the total energy is conserved. And if we think about what the potential energy, when we start a ball right there, there's only potential energy, there's no kinetic energy, and the potential energy is the mass of the ball, or the object, times G, times the height, which I'm going to take to be equal to C. And this throughout the entire thing is always going to be equal to the kinetic energy, which is 1/2 mv squared, and then plus the current height of the ball, which I will say, plus the potential energy, which is going to be equal to m times g times y. And of course, these are getting a little bit the coordinate system is getting a little bit muddled here. But if we divide through by m, what we're going to get is 1/2 v squared 1/2 v squared is going to be equal to gc minus 1/2 mv squared is going to be equal to gc. Sorry, let me write it like this: g times c minus y. Where again, I'm the y down here is a little bit different than the y up here. It's anyways. Okay, so this is what we're going to get here. C minus y is going to be the distance fallen. Okay. What that tells us then is that the velocity is going to be proportional to the square root of y. So then ds dt is equal to a times the square root of y. Okay, so now what we can do is we can use the fact that the total length of time taken, dt is equal to ds over the square root of ay. And now the total time is going to be we're going to integrate these, right? That'll give us the total time. Now ds is equal to the square root of dx squared plus dy squared. We're going to divide by the square root of ay. And now we can do something very similar to what we did in the previous video. I can factor out a dx squared, and I'm going to get 1 plus y prime squared dx divided by the square root of ay. And then so the total time taken, this is going to give us the total time taken, starting from x equals 0 to x equals b. Now here's the thing, we don't know what y is. So then what we want to do is we want to try to find the y that minimizes this. And this is where the idea of calculus of variations comes in. Calculus of variations says given some integral, we want to find the function that minimizes or maximizes that integral. And this is something that Euler, I don't know how much time we'll have to talk about in the videos, but it's something that Euler did a whole lot of work in, and it's a huge area of mathematics. And I just want to point out that it's very critical here that we have this conservation of energy, because we have this very interesting fact that says somehow if we optimize things locally, that is, if we find the shortest path locally, that is going to give us the shortest path globally. And that, in my opinion, is not something that is intuitively obvious. And in some cases, just not true. For example, if we don't have this conservation, so if we start to include things like friction, these ideas are no longer necessarily true. And in fact, this idea right here of the velocity being proportional to the distance fallen, that also relies crucially on the conservation of energy. And so anyways, this is something that we can now study, or that could potentially be studied, to find this right here. And there are other ways to derive similar equations to try to figure out, to try to determine what the shape of this object is. Now, another interesting fact is that this is also the isochrone problem, meaning if you start something from here or you start something from there, they're both going to reach the bottom at the same time, which in my opinion is very interesting and not at all what I would expect. Okay. So I want to mention a little bit about differential equations and trig functions. This is one of the things that we sort of started to talk about at the beginning of the video, or at the beginning of this week, the last video that I made. Now, if you've taken a differential equations class, you know that there's this relationship, or that there is that exponential functions and trig functions satisfy similar properties. This is something that you've seen for differential equations. So if you've taken differential equations, this idea is somewhat somewhat familiar, or is probably somewhat familiar. I think my thing is going off the edge here, so let me try to fix this a little bit. Nope, that did not work. Okay. Things are getting worse. Okay, I think that just might have to be good enough. Okay, so Euler is considering two different classes of functions. You have algebraic functions. These are going to be polynomials and ratios of polynomials, basically. And then you have transcendental functions. So transcendental functions are going to be the exponential and the logs. These are like what he had in his mind as the transcendental functions, just exponential functions and logarithms. So he knows that exponential functions are solutions to many differential equations, but some differential equations require more. And there is this beam equation, which is the fourth derivative of y is equal to c to the power of 4 times y. Now, he knows that y equals c to the power of x, and I would imagine also y equals y equals e to the minus cx are both solutions. But Bernoulli says there's got to be more because of the considerations he had. He's like, there has to be more. There has to be more solutions to this differential equation. So Euler starts to study this. He starts to think about this a little bit. And he begins to study, for example, differential equations of the form ay double prime plus by plus cy equals 0, and higher order differential equations as well, where a, b, and c are constants. And he realizes if I look at the algebraic equation, ar squared plus BR plus C is equal to 0, then I can solve this in the following way. If this is equal, if this is equal to R A times R minus R1 times R minus R2, where R1 and R2 are real, then the solution is just going to be some constant times e to the R1x plus some constant times e to the R2x. That's going to be sort of, all of the solutions going to be written in this form right here. On the other hand, if this is equal to A times R minus, let me see, I'm going to write it R1 squared plus, I'm going to write this as S1 squared is equal to 0. So in other words, if we have it written in this form right here, and let's just assume that A is equal to 1 for now to make some of the algebra a little bit easier, then I'm going to have the solution written in this form. It's going to be C1 e to the R1x cosine S1x plus C2 e to the R2x sine S1x. And I'm not sure at this point if he knew what would happen if we have a repeated root, if this is R minus R1 squared. Okay, but what he does know is he says, okay, well, this can be extended to like an arbitrary order differential equation, linear differential equation. If I look at something like a differential equation in this form right here, k equals 0 to n, ak y to the power of n, if that is equal to 0, then I'm simply going to look at the corresponding polynomial, k equals 0 to n, ak r to the power of n, and find the roots here. Now, the roots that correspond, the roots of the linear, if you factor this into its irreducible factors, so you're going to get, if you factor this polynomial into its irreducible factors, you're going to factor into linear factors and irreducible quadratic factors. The linear factors are going to give these exponential solutions, and the quadratic factors are going to give this these exponential cosine and sine solutions. Okay, so each linear factor is going to give you one solution, e to the root x, and then you're going to get these exponential exponential trig solutions, two solutions each for every irreducible quadratic. Okay, if you don't remember your differential equations class, just take a minute to remind yourself. Okay. So that's great because you get solutions and everything works. You can prove that these things are solutions and okay, so fine. What's the problem? It seems like that's very good work that has been done because now we solve more differential equations. Okay, well, Bernoulli has a question. So Bernoulli says, well, hold on a second, because these linear, or these irreducible quadratic factors, they're only irreducible over real numbers, but we should be able to reduce them over complex numbers, in which case we're going to get complex exponentials. And what's going on there? Because now it seems like we're saying complex exponentials and trig functions are the same. And Euler says it's not actually a big deal at all, because e to the ix plus e to the minus ix, for example, and 2 cosine x satisfy the same second order initial value problem, and therefore they're equal to each other. Okay, so it's like, calm down a little bit. It's a little bit strange, but they're just equal to each other. Why are they equal to each other? Well, they both satisfy the same second order differential equation. Okay, and apparently this satisfies Bernoulli. But now what happens is there had been an ongoing dispute about what is the natural log of minus x, where we're assuming here x is positive. Well, strictly speaking, this doesn't make sense because, I should say, naively or based on sort of the fundamental ways we think about logs, this doesn't make sense. Why doesn't it make sense? Well, remember, natural log of x is the thing to which you raise e to get x. So natural log of minus x is going to be the thing to which you raise e to get minus x. But e raised to any real number is going to be a positive number. Okay, so there's no way, just if you're dealing with real numbers, that this natural log of minus x makes sense. deal with complex numbers, of course, it makes sense. So Bernoulli says, well, natural log of x is equal to natural log of minus x is equal to natural log of x. Okay, and part of his reasoning is this false argument, I'm just going to say that now, that the natural log of minus 1 is equal to 0. Now, how did he come up with that? Well, he says 0 is equal to the natural log of 1. This is perfectly fine. This part is correct. And then he says, well, 1 is equal to minus 1 times minus 1. Again, we're not doing anything incorrect here so far. And this is equal to the natural log of minus 1 squared. Again, we have not made any mistake yet. But now, and this is where the mistake comes, this is equal to 2 times natural log of minus 1. Well, natural log of minus 1 then is equal to 0. Okay, so what what Bernoulli does is he says, okay, log of minus x, he sort of does exactly what Euler sort of did to him. He says log of minus x and log of x both satisfy the same differential equation, which means they're going to differ by a constant. And we know that log of 1 and log of minus 1 are both equal to 0. And so that is, if you put in x equals 1 here, you're going to have log of minus 1 and log of 1. This is not true, but this is the claim. Okay, log of minus x and log of x satisfy the same differential equation. And if you plug in x is equal to 1, they're both equal to 0, and therefore they have to be equal to each other. Okay, but again, this problem right here, this is the issue right here. Going from here to here, we cannot do this. This rule only works if the thing you're squaring is a positive real number. So this is the mistake that he makes. Okay, so what Euler does is he says they're having this conversation going back and forth between Euler and Bernoulli. And Euler says, well, hold on a second, because I've read your paper, Bernoulli, and you proved something interesting in one of your earlier papers. And the thing that you prove in one of your early papers actually gives evidence to what I'm saying being true. And so this is what he does. This is what Euler does. So I'm going to draw a picture here, because there's various variables here that are not labeled, or that are not defined. So I'm going to try to draw a circle. Okay, so we're going to have something like this. And it's going to be a circle of radius 1. And now what I want to do is draw this. This is going to be the angle theta. Let me make sure. You know what? I'm going to try to draw this circle a little bit bigger so I can draw my Greek letters a little bit bigger. Okay, so not the best circle, and I can't find my compass right now. Here it is. But I can't hold the... Anyways, okay. Getting distracted. Okay, so we're going to have this. Again, the radius is 1. This angle is theta. This is y. And, that distance there is going to be equal to x. Okay, so what we can do is we can extend the radius like this and move this up, and we're going to call this length t. Now I want to observe something here, that by similar triangles, this distance right here, this distance is equal to a. Oh, sorry. Yeah. as I have everything planned out, and then as soon as I start doing something on the board, I start to doubt myself. So this, if the coordinates of this point are x, y, this is y, and then this distance right here is equal to x. Okay, now using similar triangles, this is also kind of an interesting idea. I don't think I mentioned this before, but I really should have. T divided by this distance, t this distance divided by that distance, which is just 1. T over 1 is equal to y over x. That's just equal to similar triangles. In other words, t is the tangent, okay? And we can see that if we let theta, if we just sort of rotate this picture around, then this line right here is also going to be tangent to the circle, okay, which is, okay, anyways. So what this tells us is that t is equal to y over x. Now, if we sort of fix this diagram, notice that when t is equal to 0, then theta is going to be equal to 0, and then when t is equal to infinity, theta is going to be equal to pi over 2. So as t goes from 0 to infinity, what happens is that we get a bigger and bigger portion of this top right quarter of the circle getting filled out. Okay? All right. So what Euler is able to do, actually I think what Bernoulli does and Euler uses is the following. He says, okay, well, t is equal to y over x. And he says that the area of a sector of a circle like this, well, it's going to be theta it's going to be theta divided by 2 pi times the area of the circle, which is pi, and that's just equal to theta divided by 2. Okay, now how does this relate to things that we have in the diagram here? Sorry, I just want to check my notes to make sure that I am not going to say something wrong. Okay. But now, what is theta? Well, theta, see, this is, t is tangent theta. Okay, so this is simply 1/2. This is simply 1/2 arctan of t. 1/2 arctan t. Okay, so this is equal to the area of a segment of the circle. Now, notice what happens if I d this, if I do, compute dA, so I'm going to have to erase this, so just write this down. If I compute dA, I'm going to have dA is equal to 1/2 d arctan theta, which is 1. D arctan t, which is 1 plus t squared dt. And then, so the area of this segment of the circle, the area of this segment of the circle from 0 to pi over 2, well, it's a circle of radius 1. So I know it's a quarter of the circle, so it's going to be pi over 4. Is going to be the integral from t equals 0 to infinity 1/2 dt over 1 plus t squared. And here's what Euler continues. He says, okay, well, Bernoulli, you were talking about how would we handle this in a modern calc class? Well, I just differentiated the answer already. We know the antiderivative is arctan. Okay, but what Euler says is, well, you were telling me that we could reduce irreducible polynomials over complex numbers. Let's do partial fractions with this. Typically, we wouldn't do partial fractions because this is irreducible. We have an irreducible thing. We do this as a combination of arctan and logs. If we have irreducible in the denominator, but Euler says let's do this. Let's do a partial fraction decomposition. So we're going to have t equals 0 to infinity, and we're going to have 1/2 over 1 plus it plus 1/2 over 1 minus it dt. Well, now this is an integral that we can compute. I'm going to just copy everything and move it up here. And maybe even since we don't need the top part of that, the bottom part of that circle, we're going to get pi over 4 is equal to 1/2 the integral t equals 0 to infinity 1/2 over 1 plus it plus 1/2 over 1 minus it dt. We're going to just do the formulas here. So we're going to get 1 over 4, and from this we're going to get the natural log of 1 plus it, and since we have a minus sign there, divided by I as well, because when we anti-differentiate, we have a y there. And the minus is going to give us natural log of 1 plus it minus natural log of 1 minus it. So we're going to have this over 1 minus it. Okay, and then this is going from t equals 0 to infinity. Okay, now notice what's going to happen. When t is equal to 0, we're going to have natural log of 1 over 1, which is 0. And then when t is equal to infinity, obviously we need to do the limit of this as t goes to infinity. But the limit of this as t goes to infinity is going to be natural log of minus 1. So this is going to be 1 over 4i times the natural log of minus 1. And if you move the 4i over here, you're going to get pi I is equal to the natural log of minus 1. And if you exponentiate this, you get Euler's famous formula, e to the I pi is equal to minus 1. Okay, so this was Euler's argument that the natural log of minus 1, that the natural log of minus 1 is equal to pi I, and this is the correct argument. This is the correct way to think about things. And that was Euler's contribution here. That was one of Euler's many contributions here. Okay, so I think this is probably going to be the last video that I make for the week. But read in the book, there's some other great stuff. We've got the calculus of variations, and then we have this huge area of calculus when we get into multivariable calculus. It's very interesting. I think we might come back to some of those things, but again, I think you should read through that and get the historical context and see how things are similar and how things are different in the way that they were doing things sort of in the beginnings of calculus, in the early days of calculus, and how we're doing things now. I really think that it can be helpful looking at the historical context of these ideas to sort of understand why we're doing them and how they're working out in modern times. At least for me, this has been one of the interesting things about sort of going through some of these computations and things that they were doing.